And I would like to thank Scripps for inviting me here to visit this beautiful campus and talk to so many interesting people while I'm here. I am going to talk about math and food. See, I love math and I also love food. And unfortunately, most people seem to love food more than they love math. And that makes me a little sad. And so I like to share my love of math with everybody, using food as a starting point. Now, some people say to me, oh, is it because in baking there's lots of math when you have to scale recipes up or divide them by 2? And that's not all that this is about. It's that I use tales from the kitchen to talk about tales from mathematics to show that the two things aren't as different as you might think. For example, when you're baking something or cooking something, you might start with a recipe and you might try to follow the recipe. But when you're just cooking for yourself, you can then invent things and make things up, and then the only thing that matters is whether you like it or not. Of course, you might poison yourself, but that's okay. And the same is true of math, actually. When you get to a certain level of research, it becomes much more like cooking in the kitchen for yourself. Unfortunately, before you get to that level, you often have to pass many tests. At school, standardized tests, all sorts of tests, you jump through all these hoops where someone tells you whether you're right or wrong. And then after you've passed those tests, you finally get to see the beautiful world of research where you get to make your own things up and decide whether you like them or not. The worst thing that can happen in that world is that you cause a contradiction and then your whole world implodes. But that's okay, you just then try a different world. So the thing is that I think it's a shame that you have to pass so many tests before you get to see that other world. It would be like having to pass cooking tests before you are allowed to go and eat in a restaurant, which would be a shame. And the thing is that I've decided to bypass all of those tests and show everybody my favorite parts of mathematics that you don't usually see unless you're quite advanced in mathematics. Maybe a math major, maybe even doing a PhD in pure mathematics. And during this talk, I'm actually going to show you some things that you wouldn't usually see unless you did a PhD in pure math. So I say, why not see them anyway? Now, it doesn't mean that you're going to be able to leave this room and immediately be able to get a PhD in pure math. But I actually think that math is like art and music and food, where you can appreciate it even if you can't do it necessarily yourself. So you can appreciate eating food even if you don't know how to make it. And you can appreciate listening to music even if you can't play it. And you can appreciate a work of art even if you don't know how to make art yourself. And I think the same is true of math, that you can appreciate math even if you can't do it yourself. There is something to appreciate. And I think it's important to share, I think it's important for me to share what I appreciate about it, so that everyone can maybe appreciate it and maybe be a bit more motivated to understand what it's about really. Because it's not just about numbers and equations, and it's not just about solving problems, and it's not just about right and wrong. Sometimes people say to me, oh, well, math is all right or wrong, isn't it? It's not. There's lots of grey areas. It's more about understanding things. It's more about making connections between things than you usually get to see in school. And it's not really the same as the thing you see in middle school or high school when you have to maybe learn a lot of formulae and maybe you have to answer lots of questions and get them right or wrong. There's a lot more to it than that. Now, when I was growing up, I was very lucky because my mother is mathematical and she showed me some of the most fun and interesting pieces of math when I was very young. So I always knew that those things were there. And there are plenty of wonderful math teachers who show that to their students as well. But it's a bit of a lottery. Some children get a wonderful math teacher who does those things and some children don't. And if they don't then have a wonderful parent who shows them those things at home, then what can they do? So I'm here to be that person, to share the things I love the most about math, and that's why I've started writing books, so that I can share those things with everybody, even if you don't have someone in the family who can share it with you. And in the last 10 years, I've seen attitudes change a little bit. When I first started as a mathematician, people would say to me, oh, I can't do math, or oh, I'm terrible at math. And now people are more likely to say to me, I wish I understood math a little bit better. And so I think that the time is good now for everyone to understand a little bit more about what it is and maybe overcome previous fears of math classes. Now, as was said in the introduction, I now teach art students at the School of the Art Institute of Chicago. And what I teach them is not remedial math, and it's not the math of art and perspective and geometry. It's really abstract mathematics, as in how to think about the world in a logical way. And the art students often have come through math in school and end up hating it. And so I study what has happened to them in the past. And my classes are sometimes a bit like therapy for their past math trauma, where we can all work through it and have a new understanding. And so this is what I want to do as widely as possible for everybody. So maybe you already love math, which is wonderful, in which case I hope I will inspire you that it really is possible to explain high-level math and your love of it to people who perhaps think that they're no good at math. So in this talk, I'm going to show you some of my favorite mathematical structures, things that you might not necessarily associate with math. But first of all, I'm going to talk about Bach, and then I'm going to talk about juggling. Then I'm going to talk about hair, factors of 30, that's definitely mathematical, cake, and custard, one of my favorite things. So how are all these things mathematical structures? Well, first of all, I should tell you what I think math is. I've told you lots of things that I think math is not. So I think that math is the study of how things work. But it's not the study of how any old things work. It's the study of how logical things work. And it's not any old study of how logical things work. It's the logical study of how logical things work. And the trouble with that is that nothing actually behaves logically. I don't behave logically, you probably don't behave logically, the computer doesn't behave logically, nothing actually behaves logically. And so in order to study anything logically, we have to ignore the pesky details that get in the way of it behaving logically, so that it can turn into something more ideal. And that move of forgetting those details is a process of abstraction, where we move from the real world of actual objects into the abstract world of ideas. And that move can seem scary, because in the abstract world of ideas, you don't really have your feet on the ground anymore. You can't touch anything, you can't feel anything. And so that can, every time an abstraction happens, some people will get afraid. But the beautiful thing about it is that in the abstract world, everything works according to logic. And for some people, that's a bad thing. So if you like winning arguments by yelling, then you will not like the logical world. And unfortunately, some people like winning arguments by yelling. But in this world, that doesn't work. It only works according to logic. And the other thing that happens when you forget some details is that lots of different situations become the same once you've forgotten those details. So numbers are fundamentally an abstraction that we've kind of all forgotten that we ever did. But if you've ever tried helping a small child learn how to count, you can see that process of abstraction happening. So you can count blocks or apples or candy or something, and you go, you have one candy and another candy, that makes two candies. You have one apple and another apple, that makes two apples. And then eventually you go, if you have one thing and another thing, that makes two things. It doesn't really matter what those things are. And you go, so why don't I just call that 1 add 1 equals 2? And that's a process of abstraction right there. We've moved from things to numbers. But most of us did it so young that we've forgotten that it even was an abstraction. A lot of people tell me they fell off mathematics when the numbers turned into letters. That's another abstraction. And then there are more abstractions beyond that, where the whole idea of numbers turns into a piece of algebra, and then the whole idea of algebra turns into something else. And so it keeps going, and every time you perform an abstraction, I think you shed more light on things, but in a particular way. So if you imagine holding a flashlight at something, if you hold it very close, then the light is very bright, but on a very small area. If you hold it further away, then you cast more light, but it's a little bit dimmer, so you don't have so much detail, but you get to see a broader area. And I think that's what abstraction in mathematics does. It doesn't tell you about the details of daily life, but it tells you something broadly about how things fit together, and it sheds light on many more things at once. before you put the details back in and do the nitty-gritty of it. And to me, that's the power of it. So I'm going to start by playing you one of my favorite pieces of Bach. There's so much math in Bach that I could talk about that all by itself for maybe 2 weeks without stopping. I won't do that. This piece is from the second book of Preludes and Fugues, the Well-Tempered Clavier. Now, Bach wrote 48 Preludes and Fugues, and what happened, there's a whole lot of math even in that, because of some math, it became possible to tune instruments better than had been possible before. Before that, some notes were very in tune and some notes were very out of tune. And then it became possible to make them all sound quite nice. And so Bach got very excited and wrote a Prelude and Fugue in every key, because before that you couldn't use every key because some of them sounded terrible. So he wrote, there are 12 keys on the piano, and then there's major and minor, so that makes 24 keys. Then he got really excited and did it again, that makes 48. And this is from the second book, so I'll just start by playing this for you. piece, like many pieces of Bach, is written in polyphony, which means that there are separate lines of music that wind their way around each other, but each one is like its own melody. And so you could, in theory, get 4 people to sing it. So the first one is the one that starts at the bottom, and then the next one goes doo-doo, 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 doo-doo. And usually when you're studying polyphony, what you do is you play each line of music by itself to see where it's going. And when I was first studying this piece, I tried to understand where the polyphony was, and I got very confused. So I decided to draw a picture of it. And here's what the picture looks like. This is a very extreme abstraction of the piece of music, because I have forgotten almost every detail apart from where the lines of music are in relation to each other at any given moment. And when I drew this picture, I understood why I didn't understand the piece, and that's always the first step to understanding something, right? And the reason is that these lines of music cross over each other and they don't come back again. And that means that the soprano here would have to end up as the tenor, and the bass would have to end up as the alto. The alto would end up as the bass, and the tenor would end up as the soprano, which means it would be quite difficult to get 4 human beings to sing it. I do have one friend who can sing soprano, alto, tenor, and bass, but that's quite rare. And I realized that once I had understood how these voices interact, I could play the piece better. And this is the abstract structure inside the piece. Now, you don't have to know it's there in order to listen to the piece of music, but I feel that I can play it better because I've understood the abstract structure inside it. And this is what I think is true about understanding the mathematics inside things, that you don't have to understand the mathematics of something in order to use it. I don't understand how my computer works, and that's one of the reasons I'm not very good at it, because I don't understand how it works, so I can't make it better. If you understand how something works, you can make it better. We don't have to understand where the structural walls are in this building to use the building. But it's a good thing someone understands where the structural walls are. And sometimes people say to me, oh, well, you know, I get on perfectly well in my life without math. And I say, well, yes, but I get on better. Now, the amazing thing about this is that it's a mathematical structure. And I first studied this piece before I started my PhD. And when I started my PhD, one of the first papers I was given by my supervisor to read had structures like this in it. I didn't know that that was going to be part of my research. But these are called braids in mathematics, and mathematicians study them to see how the crossings work and which ones cross over in different places. So when it appeared in my research, which is in a very abstract branch of mathematics called category theory, I thought, that's extraordinary. I drew one of those on a piece of bark, and the date is still written on my music from when I first drew it. So this is also related to juggling. Oh, I have to point it over there. So at this point, I could do with a juggling demonstration. I'm not very good at juggling. I used to say, oh, I can't juggle. And then someone said to me, you know, that's like what people say about math. And I thought, but I really can't juggle. And then I went home, and I tried juggling just to sort of demonstrate that it really is true that I can't juggle. And I discovered I could juggle. And it was very odd. Just by thinking, oh, that's like what people say about math, I was suddenly able to do it. And there's so much psychology wrapped up in how we think we can and can't do things. And that taught me something about if you decide you can't do something, then you sort of definitely can't. So the thing is, I'm still not good enough at juggling to do a demonstration in front of an audience, I think. So I'm wondering if there's someone here who will do a juggling demonstration. Yes? Hooray! Wonderful. What's your name?
Jackie.
Wonderful. Would you like to come on stage? Now, do you think you could try and walk across the stage while you juggle 3? I've kind of revealed the next slide already, but imagine that there's a long exposure camera taking pictures of this, a picture as Jackie walks across the stage. imagine what picture that would have made? So here is actually, thank you very much. Hooray! This is an actual long exposure picture of juggling with some illuminated juggling balls in the dark. It was not me who did this juggling. When I tried to do it, it came out very wonky. So we found an 8-year-old boy at the school. He did it. So there's one that I made digitally that's like this. So you can imagine that I start with the green and the red in my right hand and the blue in the left hand. So this is a slow motion, amazing juggling demonstration. The green ball goes across like this, and as it's going, the blue one goes across like that. And then as it's going this way, the red one goes across that way, and then the green one goes across that way. And if I turn it this way up, then you see it's the same as the braid in my hair. And mathematicians study them as braids, and if we compare it with this braid, we can start to try and say things about how those braids are different. Now, I once tried to braid my hair like the Bach braid, and maybe you can see that it doesn't work at all, because you would need a band here, and a band here, and a band here. This green strand is just floating around. It's not even really doing anything. The red and the blue ones are linking together. The green and the black ones are just doing nothing. And mathematicians study these and ask questions like, are there strands that are just floating around doing nothing? That's not technical terminology. But this one is very, very tangled up, so that you couldn't move any strand particularly. And the practical result is that I can keep this in place with just this one hairband. And if I take it out and then pretend I'm in a shampoo commercial, which I sort of always wanted to do when I was little, then the whole thing comes undone. So that's a question mathematicians ask. Could you wave a strand around and make a different one? Is it just like looking at it from a different angle? How many bands would you need to hold it in place? And mathematicians started doing this just because it was interesting. And it turned out later to have applications in all sorts of places, possibly, for example, in early diagnosis of Alzheimer's disease, which is thought to be maybe something to do with brain cells getting tangled up in the wrong way because of a mutation. And then you want to be able to tell whether it's really a different tangle from the one it's supposed to be, and you can't just stick your finger in someone's brain and wave their brain cells around to see what's going on. So you need an abstract method for deciding whether two tangles are really different or not. Now, because I couldn't braid my hair like this, I made a pie instead. This is my Bach pie. It's banana and chocolate, so it's a Bach pie. So, moving on to factors of 30, which are things that are perhaps more obviously mathematical. So can we remember what the factors of 30 are? There's 1, 2, 3, 5, 6, 10, 15, and 30. Very good. That's not very interesting. It's a bunch of numbers in a straight line. I often say that we live in a three-dimensional world, so we write on two-dimensional pieces of paper in one-dimensional straight lines. And so we force all of our math into one-dimensional straight lines, when it really had natural geometry already. And I like to say also, this is why I don't like tidying up the papers on my desk, because they have natural geometry in three-dimensional space. Anyway, we can find the natural geometry of these factors by also thinking about which ones are factors of each other. And the math I do in category theory is all about putting things in context rather than studying them in isolation. And it's about finding relationships between things rather than just looking at their intrinsic characteristics. So we can think about which of these factors are also factors of each other and draw something like a family tree. Because family trees are an abstraction of a family. All they're showing is how people are related to one another. They don't show things like how tall people are or whether they are nice or not. So we can put 30 at the top as the kind of great-grandparent, and then 6, 10, and 15 go straight into it with nothing in between. 5 goes into 10 and 15. 2 goes into 6 and 10. 3 goes into 6 and 15. And 1 goes into 2, 3, and 5. And so now we see it's a cube. which I think is much more interesting than a bunch of numbers in a straight line. And this exhibits something about the relationships between factors, and we can explore what other numbers produce cubes, what other shapes we can produce with other numbers. And when I do these with my art students, I started with it as a very small, just a passing thing. They got so interested in it, we ended up spending 3 hours. I just ditched whatever I was going to do in the rest of the class and let them explore the possibilities, because they suddenly became interested in factors of numbers in a way that they had never been interested before, because it produced shapes for them. So I can actually relate this to the previous thing we were talking about, because if I take this cube and wrap it up with ribbon like it's a present, and I can make up a rule for wrapping up the present. In math, we get to make up our own rules. We can make up any rules we want and see what happens, and that's what math is. You make a world and see what happens in it. Because we're not necessarily just trying to study the real world, we're trying to study possible worlds. So I say to my students, they can make up any rules they want as long as they follow them using logic. And the worst that will happen is that they'll cause a contradiction. That's when the world implodes, but then you just try again and you make a different world. Just like if your souffle collapses, it's all right. It might actually still be quite delicious, but you can try again and make another souffle. So my rule is that the ribbon coming in from the right is going to go on top. And the ribbons are going to follow round the side of the present, and then I need a third colour coming in from over there. Now, on this one, I'm going to use the same colours starting in the same places. So it's still going to be red here, blue here, and green here, but because the faces are in a different shape, the ribbons are going to go in a different way. And I hope you can see that if I shuffle this red and blue crossing down a bit and pull this green strand up, then this braid will become that braid. So mathematically we count them as being the same braid because they're just looked at from a slightly different angle. And this is something called the third Reidemeister move in topology. Mathematicians like giving things complicated names because it makes them feel clever, because it means no one can understand them. And unfortunately, some mathematicians like making themselves feel clever by making sure no one else will understand what they do. I don't believe in that. I believe in sharing an understanding of things. So the third Reidemeister move is one of the moves that can be used to see whether tangles are the same or not, because you reduce it down to moves so that you can just perform certain moves and produce all possible tangles that are the same. So the first Reidemeister move says you just take a loop and pull it straight. The second one says you take two strings that are crossed like that and pull them straight. And this is the third one where you move a strand over a crossing. But the squares behind it are part of algebra. And that's called the Baxter Equation, which is another fancy name for something. But the point is that it's about wrapping up present with ribbon. And I also met this when I was doing my PhD. And then I thought, wait, what we've done here is we've started with a present and we've wrapped it up with ribbon. How about I start with the ribbon? Can I reverse engineer a present that will be the exact right shape to fit under that pattern of ribbons? So I thought about it, and it's a cube. And when I realized it was a cube, I thought about it in my head, and then I tore up pieces of paper frantically and stuck them together and made the wonkiest cube that you've ever seen. But I confirmed that it really does make a cube, and I don't know why. And when I realized this, I did what I always do when I first prove something in mathematics. First I went, yay, that's amazing! And then 2 seconds later, I went, I bet everyone knows this apart from me. And 2 seconds after that, I went, it's probably wrong. And then 2 seconds later after, I went, maybe it's trivial. So like a good mathematician, I checked to see if it was trivial. I thought maybe every braid makes a cube. Well, that can't be true because a cube has 6 faces. So you have to have 6 crossings. So I thought maybe every 6 crossing braid makes a cube. And that's also not right because you could just take 2 strands and go cross, 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 cross. So I don't know why this makes a cube. I phoned a friend, as you do. I phoned my friend, in fact the one who can sing soprano, alto, tenor and bass. He likes this kind of thing. And I said, oh my God, it's a cube! And he went, I think it shows that Bach was communing with the spirit of the Platonic solids. And I don't think that's what it was, but I don't know what it was. I just think it's really cool. And sometimes it's enough that something's really cool, that it doesn't have to have a specific use. Math suffers from a burden of having to be useful. We tell people they should do it because it's useful. That would be like introducing someone to your friend and going, I'd like you to meet my friend, they're really useful. Whereas math is amazing. And a lot of the mathematical breakthroughs that have happened have done so because mathematicians were simply curious. And the applications came hundreds, possibly thousands of years later. The most famous one is a piece of number theory from 300 years ago that now is the basis of cryptography on the internet, and that took 300 years. Then there's the Platonic solids themselves. The icosahedron dates back to 2,000 years ago. 2,000 years ago. And no icosahedron, that's the one that's made of 20 triangles, no icosahedron was found in the world, naturally occurring, until the 1950s. 2,000 years later, when microscopes were made powerful enough to look at the structure of viruses, and many viruses were found to have icosahedron shapes. That took 2,000 years. So sometimes it's not the application that drives us. It's just sheer curiosity, which can be more motivating to some people. So moving on to cake. Cake is one of my favorite things to make. I really like making dessert because it's not useful. It has no nutritional value, and therefore it's just for sheer fun, and that's what I like about it. Battenberg cake is a particularly British kind of cake, and I know that the Great British Bake Off has recently made it across the Atlantic, so maybe Battenberg cake will become more known over here. The point is, it's got two colours of cake, and you definitely don't want the same colour to touch the same colour of cake, because that would be terrible. But it's also a mathematical structure. So we can look at a multiplication table for 1 and -1. And so here we're going to put 1 times 1, which is 1 usually. Here we'll put 1 times -1, and that is -1. And here we'll put -1 times -1, which is 1. So it's a Battenberg cake. We can try adding even and odd numbers. So if you add an even number to an even number, it is even. If you add an even number to an odd number, odd. And if you add an odd number to an odd number, it's even, so it's a Battenberg cake. And we can also try multiplying real and imaginary numbers. Now, maybe you don't remember what imaginary numbers are. Maybe you never knew what imaginary numbers are. Imaginary numbers are that thing that happens where they tell you you can't take the square root of a negative number. And then the next year they go, okay, now we're going to take the square root of a negative number. So even if you don't know what they are, I'm telling you that they're a Battenberg cake. So therefore, if you multiply a real number by a real number, it is real. If you multiply a real number by an imaginary number, it must be imaginary. And if you multiply an imaginary number by an imaginary number, it must be real. There. It's a Battenberg cake. And a lot of math is about spotting patterns like that. And we can spot a related pattern if we think about bed flipping. And this is why I've given you all a piece of paper with A, B, C, and D on it, because that's a bed. And I have a slightly larger bed here. Mattress flipping is what we're supposed to do every season to stop our fat bottom from pressing into the same part of the mattress all year. I never do it because I'm much too lazy. Actually, mathematics comes from mathematicians being lazy and not wanting to do the same thing over and over again. So we make a theory that does it for us. I always tell my students it's important to be lazy in the right way. So if you were going to flip your mattress, obviously you would write A, B, C, and D on it to remember where you are. This is the problem with real-life math examples. They're often exceedingly contrived and nothing to do with real life. But this one makes something nice out of it, so I'll let it go. There are several things we could do, and then we can put them in a little table like we did with multiplication. So we could do nothing, 0, that's if you're me. You do nothing, and then you do nothing again. Then you stay in the A position. Or you could do nothing, and then you could do a rotation. So this is what I'm calling rotation, and that gets us into the B position. Starting again at A, you could do nothing and then flip over sideways. So I'm calling that flip sideways, and that gets us to C. And then you could go back to the A position, you could do nothing and then flop over that way. And that is D. Okay, now if you, coming down the side, says do the thing first, and then do nothing afterwards, which produces the same result, because it doesn't really matter when you do nothing. You can do nothing anytime you want. I like doing nothing. So let's think about doing a rotation and then another rotation. So if we do a rotation and then another rotation, we get back to A. If we do a flip and then a flip, so you flip sideways and then flip sideways again, you get back to A. And how about a flop twice? So you do a flop and then another flop, still A. So that tells us that if you do the same move every season, you'll just keep getting back to where you started, and you'll miss out on the other positions. Of course, now if you have one of those fancy foam top mattresses, maybe you don't ever want to turn it over anyway. So let's try doing a rotation and then a flip. So you do a rotation and then flip sideways, D. Let's try doing a rotation and then a flop. So start in the A position, you do a rotation and then flop, C. Here, a flip and then a rotation. Flip and then rotation, D. And then here, which is the whole point, I get to say flip, flop, B. And then maybe you can guess what's going to be here. C, and maybe we can guess what's going to be here. B. And now if we're good mathematicians, rather than people on the internet, we'll actually check to see if we're right. And we check by testing it out, but we are right. The main question is, how many Battenberg cakes can you see now? So there's these two, then there's these two, there's one in the middle, but there's the big one. There's the big one, the Battenberg cake, each of whose small cakes was already a Battenberg cake. Here's one. I call this the iterated Battenberg cake. Here I've put the letters on, because I've iterated the process of Battenbergification. Mathematicians are a bit like small children who like playing the same game over and over and over and over and over and over again. And once you've done it once, you might as well try and make your theory repeat itself to see what you can get out of it. So the process of Battenbergification is like painting by numbers, where all you have to do is decide what's going to go in position 1 and what's going to go in position 2. So I can say it's going to be pink and yellow. I can say it's going to be chocolate and more chocolate, because chocolate is good. I can say it's a bunny and another bunny, and I've now Battenbergified a bunny. Or I could say it's one kind of Battenberg cake and another kind of Battenberg cake, and that makes the iterated Battenberg cake. This is something that you would usually study in a higher level algebra class at university, but it's really just about cake. And here's an extreme abstractification of abstractification. Did I just make up a word? Anyway, here's an extreme abstraction of Battenbergification. So all I had to do was tell you what goes in position 1 and position 2, so why don't I just write it like that? So now I can put yellow and pink, light brown and dark brown, bunny 1 and bunny 2, cake 1 and cake 2. But what is cake 1? Cake 1 is already one of those, and cake 2 is one of these. So why don't I take the whole picture for cake 1 and put it in the 1 spot? And then I can take the whole picture for cake 2 and put it in the 2 spot. And now I have an extreme abstraction of the iterated Battenberg cake. And this is something that mathematicians call a tree, because it looks a bit like a tree. It's not as beautiful as your actual trees out there, but it's sort of an abstract version of a tree, where you have a root and you have branches. And the nice thing about an abstract tree is that you can read it either way up. You can read it as something that started at the bottom and branched out, or you can read it as some separate things at the top that came together and made something. And trees come from sticking things together, starting at the top, and it's a scheme for sticking them together. So here's an example of 2 ways of sticking together these 3 things at the top. For example, we could stick together so we do 4 add 4, which is 8. And then we could add 2 afterwards, which is 10. And usually, because we have unfortunately squashed our mathematics into one dimension, we have to use parentheses to show that this happened instead of the tree. So on the other side, this says add 4 and 2, which makes 6. And then we add 4 afterwards, which makes 10. And we have to put the parentheses on the other side in the one-dimensional representation. And we know that these are equal. We may remember that it's the associative law for addition. But it's really about moving a branch of a tree across from left to right. And the more branches you have, the worse it looks when you write it with parentheses. Because you have parentheses all over the place and you can't tell which one is which. If you write it like trees, then it has some geometry to it, which I really like. We can try this with something else. For example, if we mix egg yolks and sugar together, and then we add milk and we heat it up, we get custard. However, if we add sugar and milk together first, and then we add the egg yolks, we do not get custard. So these are not the same. And in the work I do in a higher category theory, we look at things that aren't associative, but we look at things that might be a bit associative. So it depends what you mean. The thing on the right is definitely not custard. Whereas if you do it with cake, the usual cake ingredients, the cake recipe, there we are, says cream the sugar and the butter together, and then add the eggs, and then mix in the flour, and then you bake it and you get cake. But it turns out, actually, especially if you have an electric whisk, that you can just kind of chuck everything in and go, it's all right. But there are other ways that you can do this. You could try writing out all the possible ways of branching those ingredients together, just in that order. So this is the one where you just moved one thing across from left to right. Here are all the possibilities for 4 ingredients where you keep them in the same order. Now, some of these are very different from others. This one here says, mix the butter and the eggs together. It turns out that's really disgusting. If you then add the sugar, but then if you beat in the flour, as long as you mix it hard enough, it's kind of okay. So I took all these cake ingredients into one of my art classes one day, and we tried it. We tried all the different combinations. And what we discovered at the end is that they all looked about the same, actually. But we don't have ovens in art school. So we couldn't bake them to see what happened. However, I did a visit to the Culinary Institute of America, and they do have ovens there. And we had an amazing lecture theatre that had a kitchen instead of a stage, and it had all these cameras pointing at it so that everyone could see close-ups. And I got several pastry chef students to make cake in these different ways to see what would happen. And then we baked it. So one thing that happens is that here you need 2 bowls, because you have to mix the sugar and the butter first, you have to mix the eggs and the flour together separately in a different bowl, and then mix them together. And if you're lazy like me, you don't want to have to use an extra bowl, but maybe if you're in culinary school and someone else is washing the bowls for you, then you don't mind using an extra bowl. This one, you start by mixing eggs and flour together. That's pretty disgusting too. But then once you've mixed in the butter and the sugar, bless you, it turns out it's kind of okay. But when we baked it, what happened was that some of them rose a lot more than others. So the original one is not only the easiest to make actually come together, but it also rises the most. But actually, this one and this one both rose perfectly fine. Of course, this was not a scientific experiment, so I don't know whether they actually mixed them all the same way, or whether some of them beat it particularly hard. This one was really quite flat. But the thing is, it was still like cake. So it depends how you like your cake. I quite like dense cake, and so maybe I would have liked that. I don't like it when cake is too fluffy. And all of these were definitely cake. Whereas if you do custard the other way around, it's not anything like custard. And so it depends what you mean by the same. And when you do math at a high level, you get to make choices like that you don't get to make when you're in school. And I think that once you get to make choices about things, then it becomes more something that you can take ownership of. and then you care more about it. And so I wish we taught math where we somehow allowed students to make choices about things earlier on. So when I teach my art students, I let them decide what they want to count as the same or not. And as long as they stick to it, then it's okay. If you count something as the same and then later on you don't, that doesn't count. That wasn't logical. So here, it depends. Maybe you don't care whether your cake rises high or not. Maybe you care, maybe you're not making it, so you don't care if it's hard work. Maybe you don't have an electric whisk, and so you need to do the easier way. Maybe you care that your cake batter looks like vomit halfway through when you were making it. Or maybe you don't. You get to choose. And the study of what counts as the same in different situations is an interesting part of higher mathematics, because as we study more and more subtle objects than numbers, there are many more ways in which things can be the same. So the obvious generalization of this is, of course, what if you wanted to make chocolate cake? Because I always want to make chocolate cake, which means that you have one more ingredient. So you have 5 ingredients coming in and a lot more possible combinations. And if you draw them all out, they turn out to fit together to make this shape, which someone 3D printed for me. Somewhere towards the end of the book, there's a net of it, so you can cut it out and make it. But this, it has 6 pentagon faces. Each pentagon is an example of this thing. And then it has these 3 squares that indicate something rather interesting. It means you've done something in a different order, but in completely separate bowls, so it doesn't matter. This is called an associahedron because it studies the way associativity can sort of fail but not too badly. And we study a lot of things that kind of fail but not too badly, and we look at all the different ways they can fail. I sometimes say to my students, if you're going to fail, see how many different ways you can fail. And this is a 3-dimensional shape now. If you added another ingredient, it would become a 4-dimensional shape. That's a bit harder to print. And then so every extra ingredient you make gives an extra dimension. And this is right at the heart of my research in higher dimensional category theory. So I didn't see this until I was doing my PhD in category theory. So even people who do PhDs in pure math might never see this. But it's just about chocolate cake, really. And it's a nice shape. I've unfortunately lost the other one that had a handy hook on it because they thought I might want to hang it on my Christmas tree or something in the festive colour of black. So, to conclude, what is the research I do? I vaguely alluded to it. And in the second half of my book, I talk about category theory because I decided that it's something that can be relevant to everyone. And my art students say that at the end of the class, they really see that this type of math is relevant to them, where the equations that they did in school seemed completely irrelevant to their daily lives. Mathematics is the logical study of how logical things work. And I say that that category theory is the mathematics of mathematics. So it does for the world of mathematics the same thing that mathematics does for the world. And if we unravel this, we get that it is the logical study of the logical study of how logical things work. Now you might think this is rather wrapped up on itself, but I think that logic is at the core of everything that we do. And for me, thinking logically, well, first of all, wouldn't it be nicer in the world at the moment if everyone was able to think a bit more logically? But anyway, I think of it as being the core of how we think. It doesn't mean that everything can be treated logically. But I think it's just like our actual core muscles, that if we have a strong core of muscles, then it enables us better to access and engage the rest of our muscles and use all the strength of our body. And I think that if we have a stronger logical core of our thinking, it enables us to think more clearly about all the other things as well. It doesn't mean that I think we can aim to express all of the world logically or understand all of the world logically. There are some things I think we will never be able to understand logically, and mathematics shows the more mathematics you do, just the more questions you create all the time. But my image of it is that there's a logical core, and the part that I find the most beautiful is where the logic just meets the stuff that we can't understand. And where the stuff that's way out there is too chaotic, but the stuff that's right next to it, for example, this piece of Bach makes me cry sometimes, and I can analyze why it makes me cry, and analyze it and find the structures up to a certain point. And then beyond that point, there's something else, just beyond what I can explain. And that's where I think the beauty of it lies. And I think that my aim is to put more and more things into the logical core so that it grows. And as the sphere of the logical core grows, the surface of it grows. And that's the interface between the logical things and the non-logical things. And that's where the beauty lies. So the more things we put into it, the more access we have to beautiful things.